So this video is for year 3 students, maths department, that is 300 level students. So, and we'll be checking out on solutions of power series, that is the power series solution. So for linear ordinary differential equations with variable coefficients, the most generally effective method of obtaining solutions to differential equation is the use of power series. So we use power series to determine the solutions for differential equations, ordinary differential equations, but there is a condition applied to it, that is provided that the variable coefficients are analytical functions. Shake graph. So for this condition, we have a0 plus a1x plus a2x squared dot 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 an x raised to power n dot dot dot. Now for this condition to be satisfied, we take the limit of a's of n plus 1 over a's of n when it is less than 1, that is the absolute value of x is less than r, where r is equals to the limit of a's of n over a's of n plus 1 when n tends towards infinity. So the corresponding sum of the series, since we are dealing with series, we should know the difference between series and sequence. The corresponding sum of the series is a function of x given by f of x equals to a0 of x, a1 of x, up to a's of n. So the corresponding sum, since we are dealing with sum now, we have the sum of r equals to 0 up to infinity, a's of r, x raised to power of r. So, and when we differentiate it the first time, that is f prime of x, we have this to be a1 of x plus a2 of x. Keep on going like that. So you can see we've changed our sum to be r. On differentiating this, we have r ar x raised to power r minus 1. So also for f prime prime of x, we apply the same thing. Now from 1, you can see when we insert the value of x equals to 0, we have a of 0. So from 1, f of x can also be written as a of 0 plus the summa of r equals 1 up to infinity. Now given the homogeneous equation for linear differential equation, ordinary differential equation, we have this. So to get the ordinary point, p of x must not be equals to 0, and for singular points, we have p of x. When p of x equals to 0, we have singular point. Mind you, we have the regular singular point and the irregular singular point. So in the next video, I'll be deliberating on some basic examples on the applications of power series solutions that problems on ordinary points, singular points, and all that. Again, this is also applicable to non-homogeneous, that is when we have a constant here. So it is also applicable to that. So that is that for this video.